Hello, let's go. So, welcome to the last 4 sessions of the summer term, which will be your last 4 sessions of anything, because next year you will be working. So, we will continue with variational inference. And we have discussed thus far some basic foundations. And the basic foundations essentially came down to the decomposition of the marginal likelihood into a free energy term and a KL divergence term. Okay, please close the door. Thank you. And the reason why we came up with this, of course, is because we want to, on the one hand, obtain a posterior distribution, and we want to obtain an approximation or a value for the marginal likelihood, right? So that was the fundamental aim. So this was our base inference aim. And then we said, okay, we now have a complex model where it's not necessarily that simple to compute the posterior and the marginal of the data based on a model that we formulated. So what one can always do, and this is what we spent some time on, is to rewrite the whole thing, namely the log marginal likelihood, as this sum of a free energy term and a KL divergence term, where we introduce these variational distributions Q theta or Q theta. And then discussed that this decomposition of the log marginal likelihood into free energy and the KL divergence term can be used to minimize this KL divergence, which measures the distance between this variational distribution, which and the true posterior distribution, and the aim is to minimize this distance to have a good approximation to the posterior given by the variational distribution, and that this can be achieved by maximizing the variational free energy, because the log marginal likelihood is always constant and the KL divergence is always positive. So maximizing the free energy renders the free energy a good approximation to the log marginal likelihood, so to this, and the variational distribution a good approximation to the posterior distribution. Are there questions about this? So anything that is left unclear from this basic logic? I mean, we haven't looked at examples for that and how this is now really supposed to happen, but are there questions that remain unclear about this basic logic of variational inference? No. Good. Then I assume that this is quite clear. So the variational free energy, just as a reminder, and also the KL divergence, they are these integrals over things. So the variational free energy is the integral, or this integral, where what you put in is the probabilistic model, so Py bar theta, looks a little bit like a G here, so Y, and the variational distribution, and the KL divergence, which we looked at a little bit last time, specifically if things are Gaussian, is this integral. And the focus will be very much on the free energy in the following. So we will not evaluate KL divergences, mainly, as we also discussed, for the reason that we know or want to know everything that is in the free energy, but not necessarily the KL divergence, because here we have the posterior, and the posterior we actually want to approximate. So if we already knew it, then there wouldn't be much of a point. So in the free energy we have here the model, which we know because we define it, and we have the variational distribution because no, not because, but the variational distribution is something that we can work with, or something that we compute based on the whole framework. Yeah, so these are the two quantities. So if this is somehow all clear, at least to the degree it can get clear because it's fairly general, then the aim today is to look a little bit into two basic forms of doing variational inference, which then make things more concrete. And these two things are the following. And let me just write them down. So one thing would be freeform. Variational inference, and the other one would be fixed form. And so one of them, let me just tell you what these are. So freeform variational inference is, how can one say it? It's math. That doesn't make sense. It's math-based. Yeah, but it's math-based in the sense that the variational distribution is determined by the variational inference theorem. What this is, we will discuss in a second. Whereas in fixed form variational inference, the variational distribution form is defined. What I'm talking about here is the form of the distribution. So by that I mean the type of distribution. Yeah. So in the freeform variational inference, the variational inference theorem and doing some mathematical derivation yields a form for the variational distribution. For example, it turns out that the variational distribution, so the approximation to the posterior, is a Gaussian, or it's a gamma distribution, or it's an exponential distribution, or it's a t distribution. In fixed form variational inference, you don't say let the variational inference theorem determine what kind of distribution I'm having, but from the beginning you say, okay, I assume the variational distribution is Gaussian, yeah? And then let's see what happens. So this is where the names come from. So free form, that means the form of the distribution, of the variational distribution is free and then determined by the variational inference theorem. In the fixed form variational inference paradigm, the variational distribution is assumed to be of a specific form from the outset. So here in freeform variational inference, the variational inference theorem based on variational calculus plays a central role. And everything is quite math heavy. That's just how it is. And here you actually go from a variational problem to a nonlinear optimization problem. So the free-form variational inference is very nice, but it's more relevant actually in theoretical considerations and like for toy examples. And the fixed form variational inference is more for applications, and then, for example, DCM estimation, a lot of things in SPM and so on. So the free-form variational inference is nice and fairly theory and math heavy, interesting, and goes to the roots of where this is all coming from. Fixed form variational inference is more application heavy, not that theoretically grounded, but then actually something that can be used in all sorts of things, for all sorts of problems. And definitely from the applied perspective, fixed form variational inference is happening much more and is being developed in all sorts of variations. Free form variational inference is more from a didactic perspective interesting, but then also quite tedious in terms of the algebraic manipulations that are required. So my plan is to give you a taste of free-form variational inference, so to give you kind of a overview about what's going on with free-form variational inference, so that you get maybe a little bit of a feeling, and if you feel like you're really interested in that, that you can delve more into it. Free-form variational inference also helps to explain the name, so why this whole thing is called variational, because the reason why it's called variational is because it relates to variational calculus, but I assume that you don't really know what variational calculus is, so I want to tell you a little bit about variational calculus so that you know where the whole name comes from. Fixed form variational inference is where you don't need a lot of the things that one learns in free form variational inference, but one needs other things, and this is the thing that is actually happening under the hood, for example, in SPM, when you estimate DCMs, or what people think about when they do things like stochastic variational inference these days at NIPS or whatever. Yeah? Good. Then my plan would be today first talk about free-form variational inference without going deep into the detailed math. Once I think we covered some ground there, then at one point switch to fixed form variational inference and go a little bit more into detail there, because this is actually what if you choose to do something interesting in cognitive neuroscience, would be dealing much more with. Yeah? Good. So, free-form variational inference, that's the topic then. So one thing that both free-form and fixed-form variational inference have in common is that they do what we already last time mentioned. They use mean field approximations, which is also just a fancy name for assuming some form of factorization of the variational distribution. Yeah? So in principle, these theta can be high-dimensional random vectors, so comprising many random variables. So let's say we have here, to have something now, we have m random variables, so for example 10, and we want to, of course, approximate the posterior distribution of these 10 random variables, which might be, for example, the parameters of our DCM, or 10 of the parameters of our DCM. We want to approximate them given our data observations, so our time courses of the 3 areas. What both freeform and fixed-form variational inference usually do is that they assume some form of factorization. So that means that they assume that the variational distribution can be written as the product over some of these random variables. So for example, random variables, the product of some of the random variables. So for example, random variables 1, 2, 3, and the random variables that are not 1, 2, 3. So this is supposed to mean a partition here. So if you have, let's say, 10 random variables, then S would be, it's a little weird notation, S would be 1, 2, 3, and not S or without S would be 4 to 10. It doesn't really mean anything. Usually, once you have your model really described, you know how many random variables there are, and you can say, okay, there's a subset of random variables S, and then there's another subset of random variables, and I assume that I can compute the joint distribution over the first 3 or the first S random variables and the latter non-S random variables by the product of these two. It's we just need this to get the whole thing going. It's not something horribly complex. It just means that there's some factorization assumption in the variational distribution. Because if one makes this factorization assumption, then there is a result from variational calculus that allows one to maximize the variational free energy. So remember that we have the variational free energy as a function of the variational distribution. Now, if we assume that there's this factorization over some random variables in the unobserved random variables and some other ones, then the free energy becomes a function, of course, of this product. So there are 2 ways one can do this. So on the one hand, we can just write this as now the product. The more this just follows from putting this product here for the variational distribution. What actually is the aim is to conceive the free energy not as a function of a single variational distribution, but of distributions, of 2 distributions. So the actual aim is to do what is known as a coordinate-wise ascent. So this is, of course, not the same. I mean, here the whole thing is a function of 1 distribution, and here the thing is now a function of 2 distributions. So if one would be more careful with the notation, one should have different symbols for the f and so on. But that's at this level, it doesn't really. It just makes the notation more complex and so on. So we leave it out. So the aim is to actually do a coordinate-wise ascent of the free energy by first maximizing it with respect to some of its random variables, and then with respect to some other random variables. So this is essentially like if you have a function of 2 parameters, and you plot them here, and then I don't know, maybe it looks like this, and where it's dark there's a maximum. So the aim is to first go in one dimension to a maximum, and then in the other dimension. So for example, if one starts here and we first go over x, then we might find a maximum here, and then we go in the y direction and maybe find a maximum here, and then we go again in the x direction, find a maximum here, and then we go in the y direction, find a maximum there. So that one does this kind of coordinate-wise ascent. That's the fundamental idea. And the good thing, and this is now why this coordinate-wise ascent comes in, the good thing is that variational calculus delivers a theoretical result of how to set these distributions. And this is what I call variational calculus. This is what I call the variational inference, like the free-form variational inference theory. And this works as follows. The variational distribution over the random variables in the set S should be proportional to the exponential of the integral of the probabilistic model over the other random variables. Yeah. So this is here the model. And these are the random variables, random variables not in S. And these are the random variables in S. Roughly. So this is where this whole variational inference thing comes from. So essentially, this is a solution to maximizing a variation-free energy. And it says you have to solve an integral, namely you have to integrate the model, so usually a probability density function, over some variational distributions, and this will deliver the other variational distribution. So, yeah, this is of course, do we do this? Yeah, before I tell you a little bit more about the background, because I guess this is a little bit hard to understand if you don't have any background on any of this, I will just show you the algorithm that follows from this. So that you know, that you get a feeling how this can be mechanically used. So what follows from this and how you can then actually do variational inference is an iterative free-form algorithm. Because in the end, this is all nice, and we can write up some mathematical formulas, but in the end, we of course want to implement that in some computer program, and something should happen. So we have to do something. So if we actually want something to happen, then it's helpful if we first initialize things. And what is usually done is that at the 0 iteration, the variational distribution over S and over the non-S are set to the prior distributions. Because this is something that we have already. Yeah. So these are the marginal distributions, and if it turns out that the marginal distributions and the variational distribution are actually of the same functional form, then this works, and we can set the variational distributions in the beginning to the prior distributions, and then we can use this coordinate-wise ascent by always updating one of the variational distribution. So we are now doing this for a couple of iterations, and set the E+1 variational distribution over bar theta s proportional to the integral, to this integral where we use the ith form of, oops, there's a typo. So we have the ith version we have because we set it either to the prior or from the previous iteration. So we have this distribution, so we can compute this integral and can set the left-hand side to the distribution over S to this. And then once we have this, we can update the distribution over the other set of random variables. Oops, there we use the I+1, which we get from the previous step. And then we update this. Yeah. So what this is supposed to mean is that we can actually, if we have all these things defined, we can build an algorithm that iteratively updates one variational distribution and then the other variational distribution. This is a lot easier to appreciate when you have an actual example for that in mind, and we will get to that. But for the moment, yeah, we have it at this general level, which we need first. So I guess this is all a little bit hard to understand because it's fairly abstract and there are no concrete examples. What I want to still do is give you some idea of what this whole thing is actually about and why, where this comes from. Because you see this in the literature, and you also have the term variational inference now, and yeah, I at least want to tell you a little bit about where this is coming from. And this is what I want to do now, and then I hope some parts of this will get clearer, and then when we look at an example, I hope other parts will get clearer. Let me first tell you about what variational calculus is. Does anyone of you know what variational calculus is? No. It's actually also some form of calculus that you So calculus you all know, and we will basically develop variational calculus parallel to standard calculus graphically. And it's also something that it's not the first topic that you encounter in math. Actually, it's something you might encounter that in German math together with functional analysis, so functional analysis. But yeah, it's a little bit special, although it's actually quite old. It's a little bit strange with variational calculus, but this is where the whole thing is coming from. So what I'm trying to explain here is the difference between calculus and variational calculus, and where and what this is all about. So first, think again back to your knowledge about calculus, and these are things now that you know, that are not novel. So if you want to find the minimum of a function, what do you do? And then? And then?
You calculate the second derivative?
Yeah, but if you set it to 0, so you set the derivative to 0, and if you set the derivative to 0, what do you do then? You solve for the point. Yeah, but that's important. So if just setting it to 0 means you just write that it's 0, but then you solve for actually the point that corresponds to a minimum or maximum, and then you can use the second derivative to test whether in this at this location there actually is a minimum, a maximum, or a saddle point. And this is what this little graph is supposed to show. So here you have a standard function of a real argument. So here you put in numbers into the function f. It's just this parabola, or however you call this. So it's the square with something added to it. And the aim is to find the minimum. And then since your school days, you know that in a minimum or a maximum or a saddle point of this function, the derivative vanishes. So if there is a minimum at this point x star, then the first derivative of this function in this point is 0. Yeah? So that's the necessary condition. So if there's a minimum or a maximum or a saddle point, then the first derivative is 0, which you also can see here. So I plotted the first derivative to this function, which is, I mean, if this is roughly x squared, then this is roughly 2x. And here the derivative is negative. Here the derivative is positive, and of course, because here it's the function is going down, the derivative is negative. Here the function is going up again, so the derivative is positive. That means that in this location where this is changing from going down to going upward, the derivative is 0. Yeah. So this you know quite well. Now this applies to functions, so to things where you put in. Doesn't want to draw. Functions where you put in numbers. Yeah? Now variational calculus deals with what is sometimes called functionals, and the functional that we actually have been dealing with all the time, although I have not necessarily called it this way, is the variational free energy. So let's go one step back to the variational free energy. So here we have the variational free energy, and what we put in there is a distribution and a distribution characterized by its probability density function or probability mass function. Yeah? So what we have is a function of a function. So we put a function into a function. This is why the free energy and also the KL divergence, they are sometimes referred to as functionals, to emphasize that these are not functions where you put in numbers, but functions where you put in functions. Yeah? The modern nomenclature is actually not to call these things functionals, but just to call them functions. They are just functions of functions. But I mean, if you hear this for the first time, then it might not hurt to remember that the free energy is a specific type of function, namely a functional, which is a function where you put in a function. What the free energy, of course, returns is a real number. Now, what this is supposed to show here is a set of functions. Yeah? So there are some functions in here. So for example, a function describing a line, a function describing this kind of wave, and a function describing this kind of thing. And what the free energy does, or what functionals do, is they take some form, they take some function here as an input argument and project it onto a real number. Yeah, so you put into the free energy, or a functional in general, you put in a function. And now the mathematical machinery that deals with the question of functionals, so functions of functions, and how to find the function that maximizes or minimizes a certain functional, that is called variational calculus. Yeah? And variational calculus, in essence, works on the global level very similar to standard calculus. The basic idea is that you compute the derivative of a function, of a functional, here this delta f, and at the location that this functional has a maximum or minimum, this derivative is 0. Yeah? So think again, standard calculus, you have a function, you put in real numbers, to find where this function has a maximum, minimum, or saddle point, or an extremum, or a critical point, however you want to call it. You compute the derivative of the function and then solve for the critical point. For functionals, on the other hand, where the functionals are function of functions, you do essentially the same thing. You compute the derivative of the functional, with respect to the input function, and then you solve. Then you set to 0 and solve for the function that yields this critical point. So again, because I somehow always the words come out different from what I intend. Here you have this functional f. You put in a function, that's how it's defined. To compute the minimum or maximum of this functional with respect to its input function, you compute its derivative and then set it to 0 and solve. So the logic is exactly the same, only that you're not dealing with input arguments that are numbers, but with input arguments that are functions, which also means that what you get from the procedure is not a number. So for example, for x squared, you know that the minimum is at x equals 0. For a functional, which is a function of a function, the result where the minimum is not a number, so it's not like 120 or something, but it's a function. So it's something like the Gaussian or the gamma density function, or x squared, or 10x plus 2 or something like this. These are the results for maximizing, minimizing, or finding extremal points for functionals. And of course we have this problem here because what we want to do is to find the maximum we want to maximize the variational free energy. So we want to, the fundamental problem is to find the maximum of the variational free energy with respect to its input, which are the variational distributions and their density functions. So these are functions. Yeah? So we want to find the maximum of the free energy functional. And the argument that maximizes the variational free energy is, of course, the variational distribution that we are interested in. And for this, variational calculus has developed a language and methods, and there are two things that are quite relevant for the case that we are dealing with. So if you study variational calculus, the first thing that you will come across is what is known as the fixed endpoint problem. So maybe we keep it like this. So there the idea is you should find a function that minimizes a certain aspect. Actually, have I written that down? Yeah, namely the length of the function between 2 points. Now, and there you can come up with many different potential solutions. So you can have a function that describes this, you can have a function that describes this, or you can have a function that describes this. Of course, intuitively, you know that if you want the minimal length from this point to this point, you should just go via a straight line. A straight line you can, of course, describe mathematically as a function. If you do the variational calculus and cast this problem of finding the minimal the function that has the minimal length between these 2 points, it will turn out that this is a straight line. Yeah. So if you want to look into the mathematical details of this, of course, this is all written up in the variational inference chapter of PMFN. And the problem is that you need partial differential equations to deal with it, which might be a step, but that's it's all written up there if you want to look into how it's actually looking. For what we are dealing with, we have something that is a little bit more constrained. So we have the problem that we want to maximize the variational free energy under the constraint that the function that we put into our functional of interest integrates to 1. Yeah? We want a probability density function. A probability density function integrates to 1, and this refers to what is known as the isoperimetric problem. This means that the function that is allowed to maximize or minimize, in our case maximize the variational free energy, has a constraint, namely that it integrates to 1, and this is called isoperimetric. And this then requires that you actually use concepts from constraint maximization theory, namely Lagrange multipliers, in addition to the variational calculus core equations. Doesn't necessarily make things simpler, but in the end explains where the variational inference theorem comes from. The critical thing, or the most important thing, if you look into variational calculus and you want to see its connection to variational inference, is what is known as Dido's problem. That's the problem that is shown here. So the idea is that you have a given parameter, so you have some constraint, namely that whole thing, the function that you're dealing with should integrate to 1 and has a certain length. The question is, how can you maximize the area that you enclose between 2 points and the x-axis here? And then the solution to this is that you use a half circle. This is also, all the math is written up in the PMFN chapter. The idea is that this was some kind of queen in the old days, much like Daenerys Targaryen, and she had a little bit of a land, and then she had an ox thing where she made a long line, a long rope out, and then she was allowed to have as much land as she could enclose by that. And the best thing is to use this half circle. That's Dido's problem. So that means if you really want to know where the variational inference theorem is coming from, you need to go into variational calculus and study variational calculus from beginning until you hit Dido's problem. Once you hit Dido's problem and clarified for yourself what this is about, then you can actually derive the variational inference theorem. So let me show you that. How that looks. No, richtig. So the problem is we want to maximize the variational free energy integral with respect to a function, namely our variational distribution. And this thing can be cast, this is what this is about, this can be cast as a problem in variational calculus with an additional constraint, namely that the variational distribution equals 1. So here, this is just the free energy with inputs argument, the 2 factors of the entire variational distribution. We have this side constraint, namely that the variational distribution integrates to 1. And we want to maximize this with respect to Q bar theta S. What we have to do is compute its derivative, like in calculus, but in this case it's the derivative of a function with respect to a function, and at the same time respect this constraint. So we need these Lagrange multipliers. So this is then what happens. We compute the derivative and respect the constraint, and then set the derivative to 0 to get this, which then results in this formula. So of course I know that we didn't go into details about this, and we don't want to do, but this solution here that I've shown you previously, this variational inference theorem, is a freeform variational inference theorem, is the solution to actually doing what you are familiar with from basic calculus, namely computing the derivative and setting to 0 for a more advanced function, namely a function of a function. Yeah? And this is why this whole thing is called variational inference, because it's related to variational calculus. So the problem of finding the maximum or the minimum of a function with respect to a function, and where this free-form where this free-form inference theorem comes from. This comes from finding the maximum of the variational free energy functional by using the machinery of variational calculus. The thing is, once you have this general solution here, you don't need to think about variational calculus anymore, because you have this solution. This is the solution of how to maximize the free energy as a functional, and now you can just apply it. And yeah, I think after the break I show you, or I briefly talk you through one example for that, so that you see it a little bit and maybe can appreciate it a little bit, but then you can also say, okay, and this involves a lot of math, and I want to not look into that. So let's have a break now, unless there are questions right now. No, good.